Right, so this video is going to look at a new topic. I suppose it depends when you're watching this. In 2016, this is a new topic, but in 2030, it won't be very new, or maybe an old topic. Anyway, new topic at this point to the more recent change specification, and that's the equilibrium constant KP. KC is one that at this point, hopefully, you've covered. I'm going to assume there's some sort of there's an understanding there, but KP is a new one. It's all to do with partial pressures within equilibrium and gases rather than Kc being just to do with general sort of constants. But again, it is a constant, so it follows all the rules of constants like Ka. So we've got Kp, Kc, Kw, and just K, the rate constant. So they all have these same sort of principles behind them. But anyway, if we get an equilibrium, because this is what it's obviously based around, so if we have a generic equilibrium, which we'll say is A, and B, and then we'll have C, and D. So what I'm saying is that A reacts with B to produce C and D and vice versa. So they've reached equilibrium in a closed, sealed system. And my coefficients here are little a, little b, little c, and little d. And the reason I put those in is because it's really useful. So if we were back doing the whole Kc equilibrium expression thing, we would say, right, well, Kc is the product over the reactants, the concentration of, so it'd be C in square brackets multiplied by D, and this would be the power of C, and this would be the power of D, and we divide that by A multiplied by B, the concentration of each, to the power of A and to the power of B. That is Kc. Now that's clearly not Kp because it's Kc, which isn't right, but Kp is almost identical, and it's Kp. Rather than being square brackets, we still have C multiplied by D, but now it's PC, so it's the partial pressure of C to the power of C again, multiplied by the partial pressure of D to the power of D. This is the little baby D's there, divided by partial pressure of A to the power of A, multiplied by the partial pressure of B to the power of B. Exact same in many ways. Obviously, don't confuse square brackets on Kc with these normal brackets. Don't be putting square brackets there. Yes, it is a problem because square brackets denote concentration. We're looking at partial pressure, hence the reason we have a P in normal brackets there rather than square brackets. So don't put square brackets in. It is incorrect. And also here, don't put normal brackets on Kc. This is concentration. This is pressure. Okay, get those right. If you don't get them right, you're going to have issues. Okay. But it works exactly the same in that when we come out with that value of Kp, if we have a simple example, which I'll show you in a second, we just multiply those together to our correct powers, and we multiply those together to our correct powers, and we come out with the value of Kp. And a really sort of simple question would look something like this. So we've got a nice simple question there. Now, I used this with my class a little while ago, and they had the equation. The equation for this is PCl5, and it decomposes into PCl3 and CTl2. It's a bit of a confusing one. All of these are in gas form, by the way, in the gas phase. A bit of a confusing one because you've got P, the partial pressure of PCl5, and then the P of PCl3, and then the P of Cl2. So there's a bit confusing with the P's and all that, but same principle. To start, we're trying to work out the Kp value, and we are given a temperature, and we are given some partial pressures measured in kilopascals, that being the normal unit that we're going to use. And I'll come on to a second about actually how this works in just a moment. But what we'll do here, Kp. Product over reactants, so it's going to be P, I'm going to get this wrong now, PCl3. Our coefficients are 1 in each case, so that's fine. Multiply that by the partial pressure of Cl2, and we'll divide that by the partial pressure of PCl5. We're given those values here, so PCl3 is 263. P of Cl2, partial pressure there is 263 again. Nice and easy. And then we've got 188 is the partial pressure of PCl5. So all we would do is we multiply that number by that number divided by 188, and we come out with the value of, and we'll do this live time. So 263 times 263 divided by 188, and that comes out with a value of 367.92. Get rid of that. 367.92. Now, strictly speaking here, because all our values are given as three significant figures, we should therefore give our answer as three significant figures. We work to our lowest number of significant figures given in the question. In this case it's 3, therefore our answer would be 368. Now we need to give a unit to that as well. Units here, kilopascal times kilopascal over kilopascal. In this particular instance they are going to cancel, therefore our unit is kilopascals. It's a good idea, and those people who have done maths, particularly C1, this shouldn't be an issue really, the whole sort of indices and the way those works, particularly multiplication, division, cancelling of indices and all the rest, or not cancelling of indices, but how they work with in terms of multiplication, division. If you're not very clear on indices and things, it's probably worth getting a C1 textbook, talking to a maths teacher, or hopefully your teachers at school will tell you this or help you, and just getting a heads up on how indices work. In that, for example, if we had kilopascal over kilopascal times kilopascal, this would end up being kilopascal to the -1. Now I'm not going to go into huge amounts of detail there because that's for another time, but it's just worthwhile having to get in your head around the sort of the basic concepts of indices. This is a very easy question. You could get this in an exam, and I'm going to do a question at the very end, which is a bit more of a difficult one, but it still isn't hard at all. This is a really nice, easy topic, and you want to hope that it comes up. It's all very good, this question, because we are given the partial pressures, but we may not be given the partial pressures. We may be given other bits of information, and we may have to calculate the partial pressures to then put them into our equilibrium expression to finally work out Kp. So in that sense, we may need to use something called the mole fraction. Now the mole fraction is exactly as the name suggests. It's the fraction of moles of a certain gas. So this is of a certain gas in the equilibrium system, and it's the number of moles of the gas, so whatever gas it is we're talking about, divided by total number moles of gas. So that's not just of that one gas, it's the total number of moles of the gas. So it's the mole fraction is the number of moles of a particular gas that we're talking about, oxygen, chlorine, whatever it be, divided by the total number of moles of gas in that equilibrium system at equilibrium. And so a question would look something like this for a working out mole fractions. So this question, nice simple one. It's not tying into Kp as such, but it's just getting us to calculate the mole fraction of PCl5 in this case. Now, we're told that when 2 moles, I like this question because it's got a bit of work that has to be done within it. So we're told that when 2 moles of PCl5 is heated, so initially we just have PCl5 here, phosphorus pentachloride. When it's heated in a sealed container, 2 moles of it, the equilibrium mixture contains 1.25 moles of chlorine. That is important. Now that chlorine has come from the decomposition of our PCl5. Now, if PCl5 has decomposed to produce 1.25 moles of chlorine, it must also have produced 1.25 moles of PCl3. So at equilibrium, we would have Cl2, 1.25, we're told that in the question. PCl3 must be the same because we don't start off with any, it all comes from the PCl5. Now if 1.25 and 1.25 have been produced, that means 1.25 must have reacted, but given there was 2 to start with, that means 2 minus 1.25, PCl5 must therefore be 0.75. So my mole fraction of PCl5, so it's PCl5 I'm looking at, my mole fraction is going to be 0.75 divided by 1.25 add 1.25 add 0.75. So that's going to be what? 2.5, 3.25. Do this as is. 0.75 divided by 3. That gives us 0.2307. 0.2307. Again, 3 significant figures looking at our information given. That will be 0.231, and that is my mole fraction of that. Nice and simple. No units associated with this because it's just molar numbers. There are no units here at all, so we can just say it's 0.231 moles. Easy. We can work out now from mole fractions, that's all very useful, but that still doesn't get to the point of partial pressures and Kp. We can work out partial pressures from our mole fractions. So a question would look something like this. Would be, oh, actually, no. This is how, first of all, you would work out. It's probably the easiest thing. Our partial pressure of a gas, and this is an easy one. It's our mole fraction. I'll just call it MF multiplied by the total pressure. Now, you would likely have to work out the mole fraction, but you'd be given the total pressure. So literally you just do that number before, for example, this one, multiplied by the total pressure, and that would give us our partial pressure of that particular gas. And so a question you might get, a simple question, would look something like this. And I've just realised this isn't as simple of a question as I thought. Got some nice maths here, but it's good. A bit of maths is good for you. You are going to get loads more maths in the A level, so you might as well get used to it. So here we've got mixture of 8.02 grams of nitrogen gas and 2.42 grams of oxygen gas is contained inside a sealed vessel. Given the total pressure of the mixture is 921 kilopascals, what is the partial pressure of the oxygen? Okay, so what we'll do here is we need to think, right, we've got to work out our mole fraction of the oxygen, so that's going to be our first stage, mole fraction of O2. Lay out your things you're doing nice and clearly. Now our mole fraction of O2 is going to be our moles of oxygen divided by total moles. So we're going to have to work out the moles of nitrogen, and we're going to have to work out the moles of O2, and then we can finally work out the partial pressure of O2, or really I should have just written as PO2, but we'll get there. So moles of nitrogen. Now N2 has an MR of 28, oxygen is going to be 32. So our moles is going to be mass over MR. So for nitrogen it's going to be 8.02 divided by 28, and for oxygen it's going to be 2.42 divided by 32. And we're going to work those out. We're going to get 8.02 divided by 28, 0.2864. If I was doing this in real life, I'd do this, well, obviously this is real life, but I'd do it to a much more, well, I'd keep the value as it were, to be honest, on the calculator, but I can't on this one, so 0.075625. So there's our two values for the moles. Now, our total is going to be those two added together. So what we're going to do is going to look at mole fraction of O2. Well, moles of O2 is 0.075625 divided by those two added together, which is going to be, roughly speaking, it's not going to be great, but it could be worse. Divided by 0.075625. Don't do that, you might do it correctly, that'll help. Zero point 362025, 362025, 362025. 362025. Okay, and then what we're going to do here is we're going to do 0.075625 divided by 0.362025. That's going to give us 0.208 blah 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 blah. Now that would be our part. That's going to be our mole fraction. Now I'm going to leave this value here because I want to make this as accurate as I can, even though I've done a rubbish job of it. We do our mole fraction, which is this number here, multiplied by our total pressure, which is 921. So I'm going to multiply that value by 921, and that is going to give me 192 to three significant figures. 192 kilopascals. So all I've done is this value here, which I can't remember exactly what it was. It was that value multiplied by 921, because that was the total pressure here. It's going to give me my partial pressure of O2. Not a very difficult calculation, but one again that you need to be able to do. This time you can see now moving towards the position we'd need to be in if we're going to get a more difficult question, which I'll show you in a moment. That is just the partial pressure of one part. Now we would have to obviously do that for each individual constituent if we were talking about a bigger question. I'll show you that, as I said, in just a moment. But the last thing I want to look at is, given with any equilibrium, you can have the idea of changing conditions and how that affects it, particularly how that would affect the equilibrium constant, Kp in this case. So let's pick an equilibrium. Let's say SO2 plus half O2, SO3, all of these gases, and that's got a delta H value of minus 197 or something like that. So it's an exothermic reaction. Changing concentration, how would that affect the value of Kp? Well, we know that Kp is going to be equal to SO3, nearly forgot that, divided by SO2 multiplied by PO2 to the power of half. That's my Kp value there. Now if I change the concentration, which is essentially changing the pressure in a gaseous equilibrium, I'm going to find no change. Kp is going to remain constant. The reason being that when we change the pressure, long and short of it is that the pressure therefore will go up, therefore the partial pressures of each of these things will change based on the fact that whilst the mole fractions will remain the same, because the same number of moles of each will be present. I'm trying to think with yeah. Basically, long and short of it, without getting really complicated and starting to think about stuff and starting doing mathematically, Kp does not change, and the reason is that any change that occurs here, any difference in pressure or whatever, is ultimately accounted for within movements of these numbers here, within the sulfur trioxide, the dioxide, and the O2. Now you could sit and I'm sure you can work this out. I think ChemGuide has quite a nice page where he talks about, the guy Jim Clark talks about ultimately how to actually sort of work these things through. But because this is a constant, constants are not affected by anything other than temperature changes. So from an exam perspective, they're not going to get you to prove that it's that concentration doesn't affect it. Fact of the matter is, it's a little, or pressure, little tiny throwaway question. What would happen to the value of Kp if the pressure was increased? Nothing, no change, because it's not affected by the value of changes in pressure or concentration. However, changing temperature is going to affect our value, and what's going to happen there is exactly the other equilibriums that we need to take into account, whether it is an exothermic or an endothermic reaction. So if we increase our temperature, let's do first, if we decrease our temperature, we would find that the equilibrium will shift into the forward direction, into the exothermic direction, because we've decreased our temperature. Therefore our value of SO3 is going to increase. That means the partial pressure of SO3 would increase. That means this top portion here would increase. Therefore our value of Kp would increase for this particular situation. And the opposite would be true if we increase temperature. It would move into the endothermic direction, which is this backward reaction. We would find the bottom portion here would get bigger as a result, and the overall change there would be a lower value of Kp. So temperature will affect this, and that's just ordinary sort of Le Chatelier's principle, the idea of how changing conditions changes it, and that will affect the value of Kp. That does, again, ChemGuide does a pretty good job on this one with extra detail if you want that. Temperature will change it, as I've just sort of gone through there, which is quite quick, but at this point you should be happy with Le Chatelier. Concentration, pressure, etc. won't change it. Catalyst also won't change anything. Catalyst will get us to equilibrium quicker, but it affects the forward and the back reaction rate equally. Therefore, we're going to get no overall change besides the speeds that we reach equilibrium. So catalyst's not going to do anything. Okay, this is pretty much the end of the video, but I do want to finish on one question which was taken from the specimen paper, actually, to go through sort of some more detail and the things you would get. So that question looks a lot like this. Okay, so this is the question. It's question 4.6, and this is taken from, wish they would disappear, they're annoying, aren't they? Anyway, it's question 4.6 from the full A-level specimen paper, the first one that came out, and it's from paper 1, which is where you're going to get a lot of the inorganic and physical contents. This is where Kp is going to be introduced. It's quite small, this little pointer here, but hopefully you can see. So we're calculating the value for Kp. So we're told in a laboratory experiment to investigate the reaction shown below, that's this one here, 1 mole of carbon dioxide and 3 mole of hydrogen was sealed into a container. So we start with 1 mole of carbon dioxide and 3 moles of hydrogen, and they're sealed in containers. So that's our initial substances. After the mixture had reached equilibrium at a pressure of 500 kilopascals, the yield of methanol was 0.86 moles. Now I know that that methanol has to have come from the reaction here. It cannot have come from anywhere else. So I know that if this is a ratio here of 1 to 1, that 0.86 must have come from this reacting 0.86 worth. So 0.86 of this must have reacted. This is at equilibrium, by the way, this bottom portion here. So I know that if 0.86 of this has reacted, then I will have 0.14 left because I started with 1. Now if we've produced 0.86 of this, then we must have also produced 0.86 of this. Now H2, 0.86 react. We've got a rate of we've got a thingy of 3 to 1 there, ratio of 3 to 1. So if 0.86 of this reacted because it's 1 to 1 ratio, that means 3 times 0.86 of this must reacted, which is what? Maths. I'm giving in. 0.86 times 3, 2.58, there we go. So we know therefore if we started with 3 and 2.58 of that had reacted, we must be left with 0.42. Okay, those numbers are important because they are our mole values at equilibrium of each of our 4 constituents. Now this is worth 7 marks, and ultimately we're calculating the value of Kp and we're giving it units and appropriate number of significant figures and stuff, which we'll get to at the end. But we are given no values of partial pressure, so we are going to have to work those out. Now we will need to know the mole fractions of each of these. So the mole fraction of CO2, we have to work out the mole fraction of H2, we have to work out the mole fraction of methanol, CH3OH, and we have to work out the mole fraction of H2O. Now what's quite handy is that we have our molar values here, so if we can work out total moles, then we can use that again and again. That total moles is going to be 0.14, add 0.42, add 0.86, add 0.86, which is going to come to, using again a calculator because maths has gone, Christmas has eaten my brain, 0.86, add 0.86, 2.28 moles in total. So we have 2.28 moles in total at equilibrium. So moles of CO2 is going to be 0.14 divided by 2.28. This is going to be 0.42 divided by 2.28. This one's going to be 0.86 divided by 2.28, and actually luckily it's going to be the same value for this one as well, so we'll just do that obviously once. Probably worthwhile saying it's going to be as above, it's going to be the same calculation there. So let's do 0.14 divided by 2.28, but these numbers are lovely. Look at that, 0.061403. Now I'm going to, I can't use this number as it is, it's just a nightmare. I'll tell you what I'm going to do. I'm going to be sneaky here, and I'm going to do this. Ultimately, you'd work out the mole fraction of each one, but we want the partial pressure of each one. So we need to multiply all of these by the total pressure of 500 to turn them into partial pressure. So I'm just going to do that in here to reduce some of my error that I get. Now I am going to we'll do times by 500 there, and we'll do this to 30.7017. 30.7017. Blah 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 blah. Then we'll do the times 500 column here, and that'll be my partial pressure, and we'll do that for each of these 4. So let's do it again. 0.42 divided by 2.28 times 500, 92.1052, 92.1052, 92.1052. Final one, 0.86 divided by 2.28 times 500, 188.5964, 188.5964, 188.5964, 188.5964, 5964, and the same for that one. Whew. So these are my partial pressures for carbon dioxide, hydrogen, methanol, and water. 7 marks. So it's taken a while, but it's 7 pretty easy marks. So we calculate a value for the Kp now. We need to write our Kp expression. So we're going to go Kp is equal to, now it's methanol, if I remember correctly, CH3OH multiplied by H2O divided by PCO2 multiplied by pH2, but that was a coefficient of 3 there. Therefore, we thrice it. We don't thrice it, that's a lie. We triple it. No, we don't. We do it to the power of 3 words. English, not my forte. So we have methanol times blah, 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 blah. So essentially, we're going to do these numbers. We're going to substitute these in. So we're going to have, where is it? Where have you gone? You're there. 1 point. No, I'm going to do this. Type them in right. That helps. 5964. I'm going to do that squared because that's all it is. It's the same number times itself. PCO2 is going to be 30.7017 multiplied by 92.1052 cubed. Oh, these numbers. This is not what I needed right now. Let's see if this will even work. Can I make this like... Oh, there's a history. Great. Well, that doesn't really do anything, does it? Can I make this scientific? Oh, look at that. What is this? Oh, no. No, undo. Okay, I think this will work. 1.88.5964. Oh, that is not the answer. 188.5964 squared. It's a massive number. Okay, equal. So we'll keep these numbers here, and hopefully this will work. I'm going to use like a real-life calculator. This is what I should have done earlier on. 30.7017 multiplied by 92.1052 to the power of 3. I'm feeling very, very dodgy about this. I'm not entirely convinced this is right, but there we go. It's fine. So we'll do this number divided by this number what's going on? This number divided by this number. Let's just type it in. 35,568.602 35,568.602 divided by 23,989,221.066. So I reckon it's going to give us something like 0.00014826. 0.00014826, 0.00014826, 0.00014826. Right. So let's standard form that. It's a bit easier. 1, 2, 3. So it'll be 1.48 times 10 to the minus 3. Now let's have a look. Give your answer the appropriate number of significant figures. So two significant figures are given. Oh, where's the pen? There you are. Oh no, there you are. And here, so 2 there, 2 there, 2 there. That's given to 3. Well, potentially 2. So 2 anyway is our minimum. So we need to be basically saying 1.5. Now, bear in mind, I've not checked the answer here. We may find differences because I rounded my answers and I did not use them from the calculator as you should, only because of my lack of calculator ability and showing you how I was doing on the screen. You may find there's a difference in my value and the actual answer, which I'm going to put up in a second, but we'll see. In terms of units, should have no issue there. We've got kilopascal times kilopascal over kilopascal, and then there'll be kilopascal, kilopascal, and kilopascal. Therefore, we've got 1, 2, 3, 4. So it should be, our unit is going to be kilopascal squared, but it's 1 over that, so it's going to be kPa to the minus 2. So our units here, where have you gone? kPa to the minus 2. So I'm saying something like 1.5 times 10 to the minus 3, kPa to the minus 2. And the real answer is this. Oh, look at that. Nailed it. Seriously. Unbelievable. Even with my rounding, I've absolutely destroyed this. 1.5 times 10 to the minus 3. Oh, kPa to the minus 2. So we can see this is the mark scheme, by the way. You can see they've done all the work, and as you can got for this answer, they've got full 7 marks there. Must be to two significant figures. Absolutely destroyed that. Absolutely chuffed. That's KP. Gone on a little bit longer than I expected it would, but that's a whole topic done on its own. So any problems, let me know. Ideally through like Twitter or something would be ideal. Otherwise, yeah, I hope that's been of some help.